Since I am the last speaker, I think it's a good time to thank the organizers of this workshop, which has been great, and we've all had a great time. Who are you in your audience? Thank you for staying to the bitter end. Hopefully this won't be too bitter, this talk. This is going to be joint work, based on joint work with a number of people. Dan Douglas, who's now at Virginia, and Nick Ovenhouse is at a postdoc at Yale. Haolin is a grad student. David Wilson, and even one more, Hai-Han Wu at Davis. Okay, and I thought I would start with a little appetizer, which is about the four-color theorem. This has to do with SL3, and I'll may explain why a little bit. Here's a little, so you take a planar triangulation, and you want to find a four-coloring, right? So coloring the vertices with four colors, so that no two adjacent vertices have the same color, right? Famous theorem. Nobody has a short proof. Here's a small result about that theorem. For every edge in the graph, just take a random unit vector in R3. Okay? And then for every face, you have three unit vectors in cyclic order. You can take the determinant of those three vectors, of the matrix formed by these three vectors. That's a number. Take the product over all the faces, take the expectation, and up to this constant, it is the number of four colorings of the graph. So if you want to prove the four-color theorem, you just have to prove that this random variable here has non-zero expectation. Any questions?
Is there an n-color version of it? That is, if you relax 4 colorable to 10 colorable?
I don't have a statement, but there is an SLN version, yes.
So that, presumably for large enough n, that's something you could prove, right? It's an easier statement.
Yeah.
So.
Well, yeah. I don't know what the statement, I'm not sure what the right statement is, but okay. Here's back to some familiar territory. Everybody knows what the dimer model is, maybe by now. You take a planar graph, here's the square grid. I take a rectangle, for example. I take two dimer covers, the red and the blue, except that the red one doesn't use the four corners A, B, C, D, right? And I just draw them on top of each other. Sometimes there's a purple edge, that means there was a red and a blue, but because the corners have degree 1, there's going to be some paths starting from the corners, and they have to end at the corners also. So there's sort of only two topological possibilities. They go sort of A goes to B and C goes to D, or the reverse. A can go to D and C can go to B. And you can ask what's the probability that they do one or the other. Right? You take two uniform random dimer covers, do the superposition, and ask about these paths. And of course, if you start with a square, the probability is 50-50. But what if you start with some, take some planar domain like this, 4 points on the corner, take a very fine graph. The theorem is there's an interesting. This probably has an interesting limit, which is due to myself and David Wilson. In the scaling limit, for a domain like simply connected domain with 4 boundary points, A, B, C, D, and I'm not going to tell you what the appropriate boundary conditions are, but there you have to be careful about boundary conditions. Then the probability is a very simple quantity. It's essentially the extremal length of that rectangle. If you take the domain and map it conformally to the upper half plane, then you just take the cross ratio of the image of A, B, C, D, appropriately defined. That is the probability. Okay, so there's a kind of a simple answer, and it indicates that this dimer model, has some. Well, first of all, there's some mysterious conformal invariance in the scaling limit, but not only that, there's some easy calculations you can do to get some conformally invariant quantities. What if I take 3 dimer covers and sort of draw them on top of each other, red, green, and blue? Then you don't see any sort of internal structure. It kind of percolates, and it's hard to see any kind of what kind of topological observable do you care about? Okay, so here's the after that warm-up, here's a little outline of my talk. I'm going to tell you what a multi-web is. And then I'll do a little more motivational stuff. I'll define the Kasteleyn matrix in this generality. And then there's one theorem, one main theorem, and then a few applications. OK. Feel free to interrupt with questions. I've been going kind of fast so far because I think everybody's familiar with what a dimer model is and so on. But here, I want to generalize what a dimer model is. So I'm going to take a planar bipartite graph. It doesn't have to be planar, it doesn't have to be bipartite, but for now, let's leave those in. And at each vertex, take a positive, a non-negative integer. Well, let's say positive integer. Let's call it the vertex multiplicity. And I'm going to assign a vector space, just a copy of Rnv at each vertex v. So a one-dimensional vector space here, a three-dimensional vector space there. And then, then on each edge, I want to just have a linear map between the corresponding vector spaces. So phi bw is a linear map from the vector space at B to the vector space at W. And there's such a linear map for each edge. Doesn't have to be invertible. Just if you want, you can just think of it as a matrix, m by n matrix associated to every edge. And let's call that a quiver representation. Well, I'm just going to call it a connection, even though it's not officially a connection because it's not invertible. I think the slightly more official terminology is quiver representation. But one of the special cases which we care about is when all the multiplicities are the same, n, and all the maps are invertible in GLN. Then this is called a GLN local system, or if you like, a GLN connection on the graph. Any questions about the definition? So that's the data. That's the data that, well, yeah. When you talk about the dimer model, you have a sort of a one-dimensional vector space on every edge, and you just have an edge weight on the edges. So when you talk about edge weights for the dimers, you can think of that edge weight as some sort of scalar isomorphism from one-dimensional space to itself. And when we first started talking about dimer models, they were just edge weights. But starting to think of them as a connection, in this case, a C star connection or a R star connection, really changes your perspective a little bit. And when you start to think geometrically, you realize that you can generalize things in a much more interesting way, in an interesting way. That's what I learned from Sasha Goncharoff, by the way. Think about the the edge weights as a C star connection, then all kinds of interesting things happen. Okay, so we have our graph with the connection. What generalizes a dimer cover? This thing is called an n-multiweb. Here, boldface n, the boldface here is supposed to indicate that it's a function on the vertices, non-negative integer valued function on the vertices. And a multi-web, an n-multiweb, is just a function on the edges, an integer valued function on the positive integer valued function on the edges, sorry, non-negative integer valued function on the edges, which sums around each vertex to the dimension of the vector space sitting there. For example, because there's a 2 here, I need the value of the multi-web on these 2 edges to sum to 2. Right? And sometimes you can draw that with single zero. The edges with multiplicity 0 you just throw away, and multiple edges you can think of as sort of parallel edges like that, but just the same. It's just 2 different ways to draw the same object. And omega sub boldface n, that's a set of multi-webs. That's the thing we want to sort of count. And in order for this to be non-empty, there's an obvious condition on the multiplicities, by the way, which is that the sum of the multiplicities at all the white vertices has to be equal to the sum of the multiplicities at the black vertices, essentially by the handshake lemma. Each edge with a multiplicity on it takes up as much white as black. But you also need a certain set of inequalities, just like in the dimer model. Right? In order for a graph to have a dimer cover, you need some inequalities on some Hall's matching theorem to hold. Also notice that if all the multiplicities are 1, it really is just a dimer cover. It's the same thing. Okay, any questions about the definition? Great. You guys are a good audience. Somebody give me some feedback. Okay, there's a thumb. Yeah, Sanjay.
If you take the n to be not integers, you can get fractional matchings on the side of matching, but what do you get in terms of matrices also?
Yeah, if you want fraction, yeah. So the question was, what happens if you want n to be non-integer? I don't know. I didn't extend the thing in that direction yet, but that's a good job for you. Yes?
When you say that the proper name is clear representation, does it mean that there are mutations involved?
Does that mean there are what?
That one can do mutations. I believe that you consider just the standard clear like divider or something like that, and then the question whether you can mutate.
I don't know. So in the case n equals n, when n is constant, then yes, there's some urban renewal you can do. Did you have a question?
It's about the quiver representation, so you don't have directionality here.
Oh, if the graph is bipartite, yeah, maybe I should have said it's important to orient the edges from black to white. I forgot to say that. Let's go back. Right, you want to. This matrix is 2 by 3, not 3 by 2, because I'm gonna. I should have written it down somewhere. Orient all the edges from black to white. So there's a map going this way, but there's not a map going the other way. So this is a map from a 2-dimensional vector space to a 3-dimensional vector space.
It's written there, but
What?
You wrote it actually.
Oh, yeah, yeah,
You wrote it.
yeah. These are all oriented from B to W. Okay, so here's our main theorem. We're going to find a certain function on a multi-web, which is called the trace. It's not just one per multi-web. It's not what we're counting. We're counting some other complicated, slightly more complicated function, which we call it a trace, even though it's not necessarily the trace of a matrix. But it is a function which depends on the connection and depends on the multiplicities. And for each multi-web gives you a real number, if it's a real number. And the theorem is that there's a certain matrix, the Kasteleyn matrix, whose determinant counts the sum over all multi-webs of the trace, up to a sign. Okay, I apologize for mentioning the 6 vertex model. I think everybody else has done it this week, but here it is. The 6 vertex model, right? This model of, well, you know what that is square ice. You pack oxygens and hydrogens in the square grid in this way. There's an oxygen at every lattice point and 2 hydrogens along the edges. We can model this as multi-webs, as counting multi-webs. So what you do is you take this graph where all the vertices of Z2 are white, and then you put a black in the center of every edge. And then you put the multiplicities at the white vertices are 2, and the multiplicities at all the black vertices are 1. Then what does a multi-web look like? It looks exactly like that, right? Every oxygen has degree 2, every hydrogen has degree 1. Okay, and if you want, Philippe mentioned the 20 vertex model. You can also model that in a very similar way with white vertices of degree 3 and black vertices of degree 1, just like that. Okay, and so the part of the theorem is that you can count square ice configurations and 20 vertex model configurations through some determinants. And of course, you don't get everything, but you do get all the free fermionic versions of these models through this theory. Okay, how do you count single dimers? Well, in case you have, if you have a planar bipartite graph, there's a certain matrix called the Kasteleyn matrix, whose determinant counts the number of dimer covers. And what matrix is it? Well, let me just tell you one small thing about this, which is when you start thinking about your edge weights as connections, you can think about the Kasteleyn matrix as just the adjacency matrix, but with a certain connection on it called the Kasteleyn connection. And the Kasteleyn connection is a plus or minus one connection, plus or minus one value connection, which has a certain monodromy condition around every face. A face of length L has this monodromy minus 1 to the L over 2 plus 1. For example, a square face has a monodromy minus 1. And if you think about it that way, then you don't have to worry about gauge transformations. You just need to take a connection in this class. Okay, so here's our theorem again. Let me tell you about the left-hand side before I tell you about the right-hand side. I still need to define the Kasteleyn matrix, and I still need to define the trace. At least we know right now what the thing we're summing over is. So what's the Kasteleyn matrix? We have our bipartite graph. We have our multiplicities on the dimensions of the vector space at the vertices, and we have our matrices on the edges. So we do the kind of obvious thing, which is you take the adjacency matrix and you replace each entry with the corresponding matrix. And I should have said BW, not WB, I apologize. Every time two vertices are adjacent, there's a matrix on that edge, and you take your Kasteleyn matrix. But then what you're going to do is replace each matrix with its array of numbers, with its block of numbers. That's how you get from K to K, this thing K tilde. K tilde is a square matrix of scalars, of real numbers, whereas this K without the tilde is just a matrix of matrices. So you see that along this edge, for example, you're going from a two-dimensional vector space to a one-dimensional vector space. So A is a 1 by 2 matrix, and you put it here in the first two columns in the first row. And you also have to put these signs in. The signs are coming from the Kasteleyn connection from before. Right, so because the total multiplicity at whites is equal to the total multiplicity at blacks, this K tilde is a square matrix. Now, a square matrix of real numbers, it has a determinant. That's what goes on the left-hand side. It's kind of the follow your nose kind of thing. What else would you do? Okay, good. I have to tell you that, right? That's the last ingredient in this theorem is the trace. How do you find the trace of a multi-web? If it's a dimer cover, you just take the product of the edge weights. So, but what do you do in a more general case? So here's, right, remember what a multi-web is. It's this set of multiplicities on the edges. And so let me first assume, for the sake of this definition, that all the multiplicities are ones or zeros. The definition is, and then I'll tell you what to do in the general case. So, and this is a sort of a tensor network definition, so, but it only takes one slide. All right, so we have at a vertex of this multiplicity n, right? We have this there are n edges of weight 1, of multiplicity 1 around it. Okay? And I'm going to associate, there's a vector space, and there's a vector space of dimension n sitting at this black vertex. I'm going to put a copy of it, v1, v2, and so on each sort of half edge around that vector space, around that vertex. Right? So I have a bunch of different vector spaces, copies of Rn. And let's fix a standard basis for the Rn, okay, E1 through En. Sorry, there's a lot of n's here, but, and now I've got n different n-dimensional vector spaces. I take their tensor product, and I'm going to define a particular element of that tensor product called the codeterminant. And here's the definition. It's an element in this, right, tensor product of n-dimensional vector spaces. You sum over the symmetric group, Sn. You take the sigma 1 basis element of the first vector space, tensor the sigma 2 basis element of the second vector space, and so on. and then you multiply by the signature, and you sum. It looks kind of like a determinant, but it's not, because it's a map from, it's an element of this big tensor product. But it does have the property of being invariant under SLN base change. If I do a gauge transformation at this vertex by multiplying by a matrix in SLN along every edge, this codeterminant doesn't change. So in that sense, it's a SLN invariant quantity. It's a unique SLN invariant quantity up the scale.
So if you act on this tensor product by the symmetric group, then is this simply the the one-dimensional
Invariant. That's exactly the one-dimensional SLN invariant in this tensor product. Exactly.
Or it's anti-invariant for the symmetric group?
What?
It is the thing that corresponds to the end sign representation of the symmetric group acting by permutation.
Yes. Okay, so we could do the same thing at a white vertex, but I want to interpret things at a white vertex using the dual vector spaces, R to the n W dual. Now we at each black vertex I have a certain vector in this tensor product. At each white vertex I have a certain dual vector in the dual tensor product in the tensor product, and now I could just contract along every edge using the matrices along the edge. So I take the tensor product over all the white vertices. That's a vector in the tensor product of all the vector spaces at the white vertices. Same thing over here with the black vertices, and I just sort of contract using this first, right? In this vector space, I have one tensor component in V1, and I can map that over to this side using the map, and then I can contract with the dual element over here. So I can just contract the tensor indices two at a time and eventually get a number. So this is kind of, in one sense, it's very clear. It's very clean. It only takes that many symbols, but it's also very opaque, right? It's very hard to see what's going on because these are, huge, exponentially large quantities, and you're contracting them all.
But if you think of this in terms of fermions, right? This is just the highest occupancy state, right? At each.
Yes.
Right, and so this is just the induced, right?
Right. In some sense, it's the most natural thing to do, but from a sort of combinatoric point of view, it looks kind of like a nightmare because there's so many symmetric groups flying around.
So sorry, but the middle tensor product in the bottom line depends on the multiweb, right?
Depends on the
connection.
Depends on the multiweb, right? That you choose.
The multiweb is the one determining which edges here participate in the tensor product. There's some edges of weight 0 which don't participate here. So the multiweb comes from the fact that this is a tensor product of length n.
So I'm trying to relate this to usual
Which you put.
usual webs, and
Sorry, go ahead.
usual webs they represent these SLN invariant functions, right?
Yes.
Of a bunch of vectors. So how is this related? How is your thing related to the usual webs?
It's the same. Yep. The only difference is this. Okay, so how do you do it for a multi-web? Right? If you have some edges of higher multiplicity, ME, you just replace them with a bunch of parallel edges, ME parallel edges, and then if there's for the connection there, you put the same matrix on every edge, you take the trace, and then you divide by ME factorial. So the only difference, if your web is not simple, if you have some edges of multiplicity bigger than 1, you just divide by the appropriate combinatorial factors, and then everything works out. Okay, and if you were paying attention, you might notice that I had to choose if n was even, I had to choose a particular order, a starting point for this order here, because if I change where I start, then I might get a sign in here, and that's what that little symbol means. That little symbol is called a cilium, and it tells you where to start you need a total order for the edges around the vertex, not just a circular order, a linear order. So that's the role of the cilium, tells you where to start your order. That's not a big deal. I shouldn't have even mentioned it, but people might get upset. Okay, and here's a very simple example for the square ice. Here's one component of the multi-web for the square ice sitting at a white vertex, right? There's some two neighbors. And remember now, on each edge, you have this, well, 2 by 1, I mean, is that a 1 by 2 vector? Yeah, it's a 2 by 1 matrix going from one-dimensional vector space to a two-dimensional vector space. So, if I'm trying to compute the trace of this part of the multi-web, it just becomes, if you just follow through the definition, it's not very hard in this case, it just becomes the determinant of the matrix formed from those columns. So the trace of this component is that determinant. And then, for every molecule here, you have a different 2 by 2 determinant, and you just take the product of them all, and that gives you the trace of the big web. Yeah?
How many parameters can survive after you define this? Is it like, I don't believe it's 8 parameters per vertex.
That's right, because there's some SL2, in this case, SL2 invariance, right? Which, well, in fact,
so how many parameters do you get at the vertex? 4.
At a vertex? Well, you get the, it's like the 6 vertex model with one relation. With the Plücker relation. So really 5.
It's 4 because you can also.
There's some global scale, right? So if you want, by the way, all your traces to be positive, right? If we want to do probability on these objects, we would like every component, every web to have a positive trace. And so, the traces will be positive if you look around each white vertex, there's these 4 2 by 1 vectors. You make them into a 2 by 4 array. What we need is that all the Plücker coordinates of this array are positive, which means that matrix is in the totally positive Grassmannian, or at least totally non-negative Grassmannian. That will guarantee that every configuration has a positive weight. And probably what you can see is that what I'm describing here is the free fermionic subvariety of the 6-vertex model. Because of all the different molecules, there's 6 possible molecules, and there's one Plücker relation here, which defines the free fermionic subvariety. Okay, and of course you can do the same thing with the triangular ice, the ammonia ice, NH3 ice. Around every vertex, you've got a 1 by 3 vector, and then each molecule has 1 nitrogen and 3 hydrogens, and the trace now is the determinant of the matrix formed by the 3 columns, the ones pointing in the direction of the arms. And those are also Plücker coordinates, and the traces are all positive if your element is in the G36 positive Grassmannian. So that gives you a nice subvariety of this 20-vertex model, which is free fermionic. Yeah?
Is positivity a strong requirement if you go to non-planar graphs? Or is that an easy thing to have?
For non-planar graphs, it becomes more interesting, just like in the dimer case, right? Non-planar graphs, you can't really count dimers all positively, but you can do it depending on the homology class. There's a sign depending on the homology class. There's something similar going here, but it's a little bit complicated. So let me not discuss it here. Was that your question?
Are you aware of choices where you would have an all positive measure?
On a non-planar graph, no. I think you have the same issue that you have for the single dimer model. In fact, I know you have the same issue for the single dimer model, which is that as soon as your graph contains a K33, you can't find the signs so that everything is positive. Okay. Oh yeah. If never mind. Ask me later. Okay. By the way, there's a version of this theory for non-bipartite weights. Non-bipartite graphs. You take let's set G be a not necessarily bipartite. This is work in progress with Hi Han, Wu. Suppose you have a not necessarily bipartite, but still planar graph. Now we're going to take all the multiplicities to be the same, but an even integer, 2n. And our connection is going to be a symplectic local system. So we have a symplectic matrix on every edge. And then there's a certain matrix, right? I'm not calling it K, let's call it H, it's an antisymmetrical matrix whose Pfaffian counts the traces of webs. The definition of a web is the same. The definition of the trace is essentially the same. Tiny details different, but right. What can I say here? I don't want to say too much in the interest of time, but the H matrix is kind of like this. The Kasteleyn, it is the natural analog of the Kasteleyn matrix for non-bipartite weights. In fact, if n equals 1 here, so you're counting, so 2n is 2, and you are indeed, and you take the identity connection, then you're just counting double dimers on this non-bipartite graph. So this is kind of the correct matrix to, well, okay. I'm starting to be stressed for time. That's why I'm not speaking coherently. But what you do is you take the adjacency matrix with the phi's in place, but then you multiply every entry in the matrix by j on the left, where j is the matrix of the symplectic form. And then you can see through a very simple string, which involves the fact that phi is symplectic, j phi inverse is phi transpose j by this rule, that the H matrix is antisymmetric, which allows you to define, so the Pfaffian is well defined, and that's what you get. Okay, so let me not talk about that. Let me just go to the applications. And I think I have some time to talk about this. So here's the sort of first application to SL2 connections. Right, so now we're going to talk about boldface 2 multiweb. So every vertex has dimension 2, right? And of course, a 2 multiweb is the same thing as a double dimer cover. It's just what you get by superimposing 2 dimer covers on top of each other. And I probably should have just made everything black here. You're not supposed to remember the colors. When you take a 2 multiweb, it's not a colored object. It's just every vertex has degree 2, and some vertices have doubled edges with them. So sorry, ignore the colors in this picture. It should have been just black. So that's a 2 multiweb. And the interesting thing about 2 multiwebs is that the trace that we defined for 2 multiweb can be written as the product over the loops. And for each loop, you get the actual matrix trace of the monodromy of the connection going around that loop. So now the connection is invertible because it's an SL2. Every matrix is an SL2. And for every loop, you can just compose the connection around that loop to get the monodromy, phi sub gamma. And then you could take the actual matrix trace to get the component of our trace associated to that loop and take the product over all the loops. So I probably should have used a different letter here. This is the actual matrix trace. That is our web trace. The web trace is a product of matrix traces in this special case, SL2. Not true in general. For example, if the connection is just the identity connection, then every loop gets weight 2, because the trace of the identity map for SL2 is just 2, and so the probability, and you can make a probability model where the probability of a multi-web is just 2 to the number of loops, the trace of the web divided by the partition function. So that's the standard probability measure that you assign to a double dimer cover.
So do you count shortest loops here in this number of loops?
No, the double edges count 1.
Sorry, so what is the trace for the GL2 connection? Like the left-hand side is still defined for the, if you measure the GL2.
For a GL2 connection, you write each element in GL2 a real of the determinant times something in SL2, and then you take the product of the SL2 matrices, and then you multiply by the
But how do you pick a direction of a loop?
Right. So you have this GL2 element on an edge, and if you go that way, you get phi, and if you go backwards, you get phi inverse times determinant of phi as and you just take the product of okay. So the determinants kind of fall out. And in particular, if they're if it's GL1, if it's just 1-by-1 matrices, then you do get the product of the edge weights around the loop. Okay, so how do we analyze this? So one of the reasons we started thinking about this, or I started thinking about this, is to try to understand something about this double dimer model, where you just take two uniform dimers and superimpose them. What can we say about this structure of this set of loops? This is still something that we don't really understand very well. But we can use this connection to probe the loop structure. And the way you do it is you puncture some of the faces. For example, ping, ping, ping. I think of my graph as lying now on this punctured surface where I've punctured some faces. And I can ask a question of the type, what is the probability that my 2-multiweb has a certain isotopy class in the complement of those punctures? Like, what's the probability that there's a loop which winds around these two punctures and another loop which winds around that puncture? Okay, that's a kind of a non-trivial thing to compute, as sort of not a local event. Well, so here's how you manage. Now I'm going to choose a connection which is a flat SL2 connection on the graph. Flat meaning around every unpunctured face, the monodromy is trivial. Trivial monodromy around contractible cycles or contractible faces, but not necessarily around the punctured faces. Then, when you have a 2-multiweb, what is the trace? Well, if you've got a flat connection, you can ignore loops which don't surround any punctures. Those just contribute 2. But then the loops which do surround punctures will pick up monodromy from the connection, a non-trivial monodromy from the connection. So you can kind of write the trace of your web as what you had before times some non-trivial quantity which depends on the flat connection. So the trace now kind of can be used to detect the homotopy type of the loops. And in fact, it's a theorem of Fock and Goncharov that the traces of these simple closed curve systems, as you vary the connection, the traces form a regular function on the whole SL2 character variety, the space of flat connections on the punctured surface. So sort of to interpret the theorem, when I take my Kasteleyn matrix now, it's determinant, and this is the theorem, it's a sum of traces. But now each trace, each web has a trace which only depends on its isotopy class in the complement of the loops. So you can instead write this sum here as a sum over simple closed curve systems, isotopy classes of simple closed curve systems, and then the coefficient is the trace times C lambda, where C lambda is the number of configurations which have that particular isotopy class. And from the Fock-Goncharov theorem, in principle, these C lambdas can be extracted from the determinant. So maybe it's good to just give the application here so you can see what's going on. Suppose my surface, here's the simplest application, an annulus. Let's take an annulus. Our graph is an annulus, or if you like, I just puncture a single face of my graph, my planar graph. Then, well, okay, that's not what I'm going to do, because I want to take a scaling limit of this. So imagine taking a very fine square grid in this annulus and ask, what happens, how many loops in my double dimer cover go around the annulus? Right? Of course, my double dimer cover is going to have a bunch of small loops, but there'll be some which go around, and I want to know how many there are. And it turns out that this is in the limit of the scaling limit as the mesh size goes to 0, this distribution only depends on the conformal modulus of that annulus, and it has kind of a very pretty formula. The probability that you get exactly J curves, if you make a generating function out of those probabilities, has a beautiful kind of theta function expansion. Here Q is the e to the minus pi tau. Tau is the conformal modulus of the annulus. So this formula is so pretty that I wanted to extend it to other Riemann surfaces, but just very hard.
Well, but presumably those are not explicit theta functions, right? For other Riemann surfaces.
Well,
At least you can connect them to known theta functions.
there are theta functions for other Riemann surfaces, yeah. And there's some sort of modular invariance and so on. So
They don't have this product formula, right?
well, maybe not a product formula, but some formula involving theta functions would be great. Okay, so let's go to the SL3 now. This is the picture you saw. What do you do with SL3? Because when I superimpose 3 dimer covers, it's just kind of a mess. You don't see any large-scale structure. Everything is connected. SL3 has some magic property which allows you to reduce, which is a notion of reduced web. Did somebody talk about reduced webs earlier this week? I lost track of who has talked about. Anyway, the idea is that secretly there's a spine in this picture, right? A colored 3-multiweb. If I have an actual coloring of the web, like in the previous picture, there's a spine which connects the boundary points together. And even though the spine itself is not really canonical, its topological type is canonical. How it connects the boundary points together is something that is a measurable function of the coloring.
You still impose something on some of the dimer coverings about the corner?
Oh yeah. I kind of screwed up this picture, so don't look too closely at this picture. But the idea is you have certain points on the boundary where there's a single, only one dimer, only one of the dimers is covering there. Like there's a little red thing sticking out at various points, and then the other 2 dimers are in the interior. So there's some boundary issues, boundary conditions, where the spine is supposed to end up. Okay.
How do you get the path? You follow red and you choose another of the 2 colors?
No, I didn't tell you how to follow the path. Right? There's some secret which only I know. Well, this picture is just sort of an illustration. It's not supposed to be, correct. Well, that's what I'm going to try to explain. Okay. First of all, we have these 3 multiwebs, right, which are a sub part of my graph, right? Some edges have multiplicity 3, some edges have multiplicity 2, but the multiplicity 2 edges have multiplicity 1 edges next to them because the sum has to be 3. So there's some chains consisting of edges of multiplicity 1, 2, 1, 2, 1, 2, and then there's some vertices of degree 3 with 3 multiplicity 1 edges around them, and then there's some triple edges, and then so that's what our typical multiweb looks like. There's an associated abstract graph, planar graph, which is the web, right? Which is a degree 3 graph, and it may have some floating components. Right? You just keep the degree 3 vertices here, and every 1, 2 chain just becomes a single edge in this abstract web. And we say that a web, well, and A4, well, it applies to webs, multiwebs too. A web is reduced, also called non-elliptic, if there are no contractible faces of degree less than or equal to 6, unlike this case, right? So if there's a face of degree 2, 0, 2, or 4, it's not reduced. But there's a way to reduce a web. So let me come back to that theorem there. There's a way to reduce a web using some so-called skein relations. Every face of degree 0, which is just a loop, you can throw it away and multiply what's left over by 3. If you have a face of degree 2, you just remove it, and like multiply everything by 2. And if you have a square face of degree 4, you can replace it with this, connected to the rest of the graph here. You can replace it with that or that. Okay, so there's some web reductions, and those web reductions preserve the trace, right? If you have some multi-web on the left, you can replace it with a linear combination of multi-webs on the right, and the sum of the traces of these guys equals the trace of that guy. So that's what I'm saying here, right? If I have a multi-web M, its trace can be written as a sum of reduced webs, well, with some coefficients. And the sum is over just isotopy classes of reduced webs here. Here it's on the left it's a multi-web. On the right it's just an abstract web, which is reduced. So if you have a web on a graph on a surface with a flat connection, then you can replace each trace with this linear combination of traces of reduced webs. And the nice thing about reduced webs is they do form a basis of the representation of the character variety. That's what the theorem of Shikora and Westbury, this is, anyway, around the two in the forgotten what the date is there. Anyway, let's say 2010, roughly, plus or minus 5. The traces of reduced, that is non-elliptic webs, on a surface with a flat connection do form a basis for the regular functions on the character variety, which means that, well, we can do what we did for the double dimer model. When we take the determinant of k, this is a sum overall of traces of all multi-webs. Now we can rewrite this as a sum over reduced webs with some coefficients. And then we can ask what these coefficients are as a function of the graph. I don't know, maybe that was too fast, but here's a sort of an application again to our annulus. On an annulus, turns out that every reduced 3 multi-web, there's sort of, on an annulus, it just comes in two flavors. It's a loop which goes around, but it may be a sort of a 1, 2, 1, 2, 1, 2 loop, or a 2, 1, 2, 1, 2, 1 loop. So there's sort of, you can think of them as having 2 different orientations. And so if I have my graph on an annulus and I sort of take the scaling limit, well, the determinant, first of all, can be written as a sum over reduced webs, and every reduced web has some number of loops going this way, some number going that way. So there's, and the trace of each component is either trace of the monodromy around the annulus or its inverse. And so in the scaling limit, you again get this pretty product formula for the, with the coefficients c, I, j are counting configurations with I loops going one way and j loops going the other way. But, it's a little bit frustrating because if I draw the triple dimer cover on that thing, it's very, how do you figure out what I and j are from that triple dimer cover? That's a little bit non-trivial. And I don't have a very good answer for that. But when you have a boundary, so the annulus didn't have a boundary. Here's a case with boundary where things are somehow a little bit more concrete. What I did was I took a large domain in the plane I chose six boundary vertices, 3 whites and 3 blacks, white, black, white, black, white, black. And then there's a way to take three dimer covers, which I superimpose each other, and then secretly there's that spine, which I haven't told you how to create yet. But you draw that spine, and one of the reduced webs has a hexagonal face here with 6 legs. It has this kind of topology here. And you can compute in the scaling limit the probability of that event. Not really surprisingly, it's a conformally invariant quantity. Here it is as a function of the complex, these boundary points, Z1 through Z6. It's some product of cross ratios. It's clearly Möbius invariant. And you can imagine it for any other planar domain as well. There are a bunch of other reduced webs here. There's like 6, I think, total for these boundary conditions, 6 possible reduced webs. They each have some expression kind of like this.
Sorry, You take a conformal map from the square to the upper
Yeah,
half
if I take this conformal map to the upper half plane, and I looked at the image of these 6 points, this would be the probability of this event, which I think in this case comes out to be like 4%. I mean, I had to run this simulation like 100 times to get one which, or maybe like, I don't know, 25 times before I got one with a hexagon, because the other ones had some other connections. Thank you.